Lee will give us a talk on Fray, an efficient general-purpose concurrency testing platform for the JVM.
Thank you for the introduction. So, hello everyone. My name's Leo and also Al. And today we're talking about how we test concurrent programs in Java. And again, concurrence bugs are one of the notorious difficult to detect and diagnose. And this is old topic, but still really hard to do in real world. And the question we're trying to answer is how to test concurrent programs. Well, you may ask, hey, isn't this problem already solved? I'm writing Rust or I'm using Tzen, right? True and false, right? If your program has bugs caused by data races, yes, using Rust and other fancy tools like OxCaml and thread synthesizer may help you to prevent those issues. But the issue I'm talking about today, such as deadlocks, atomicity violations, and other older violations, they are not necessarily caused by data races. And the question, to give you some example about what does those bugs look like, let's look at this simple bank account example. I'm implementing this withdrawal method, and I'm trying to call this withdrawal method into threads separately. And to do this, I can come up with a schedule where I let both threads to enter, to read the balance from the shared variable, and I do the condition check so that both threads will enter this true block. And then I let one thread to update the balance, and then the other thread to update the balance again. With this, I'm allowing two threads to both perform the transfer method, withdrawal method. And you can see that there's no data race in this program, but you still have this bug that is called atomicity violation. Well, this is not a new problem either. There are actually tons of research papers trying to implement fancy algorithms to identify this kind of bugs in concurrent programs. Well, this is true that you can use this algorithm to find bugs in program like this, but the question I'm asking today is how can you use this algorithm to analyze softwares like Kafka, Guava, and Lucene? In fact, developers aren't using this. Developers are still relying on simple unit tests to test their concurrent software. And this is a GitHub issue I got from Lucene, where they saw a concurrent bug in 2012, and in 2019, they saw the same bug again. And this time, they were saying they believed they found the root cause of this issue, and the way they test their software is just to run the software 20 times, and they observed no failure in their test runs. They believe the test was fixed until in 2021, the same failure was observed again. Well, running simple tests in a loop isn't really a good way to test your concurrent software, right? Then what is a good concurrency testing? And we do have some requirements. We don't want non-determinism. And we also want efficiency. That means that we want to control what threads to run given a time, and we also need to make sure the execution is deterministic. And the answer is not new either. We all know that controlled concurrency testing is something we want. And I'm not the first one who implements the controlled concurrency testing. In fact, in 2000, NASA has already proposed this idea about Java Pathfinder, which is a model checking tool that allows you to model the concurrent behavior of a Java program. But why aren't developers using this? And to understand applicability, we actually put two requirements to make a tool really applicable. And the first axis is expressibility, meaning that can I use this tool to find certain bugs? I mean, if your tool can only run a very limited number of programs, I can't really use them to analyze to application like Kafka. The second thing is efficiency. How long does a tool take to find certain bugs? In the previous example, you can see that running the test again and again may find a bug. It just takes 3 years. I can't really use them to test my concurrent software. So by putting all the prior work in this coordinate system, we notice that none of them are trying to achieve both expressibility and efficiency at the same time. So today, I'm going to talk about Fray and to discuss how Fray solved this problem. The high-level intuition of Fray is very simple. It tries to put some stop signs in your application so that your application will run in sequential order. Why am I doing this? The reason is that in Java language, it gives you this nice property called DRFSC, meaning that if your language, if your program is data race free, it gives you this sequential consistency, meaning that you can represent all possible concurrent behavior of your program in some sequential execution of the program statements. Once I have this sequential execution, if I'm able to control the execution of the program, then I'm achieving the determinism. So now I'm having a very simple loop to test my concurrent software. At the very beginning, I stop all threads, and I will check which thread can run based on the semantic of my concurrent software. And I pick one thread to run until either the thread hits another stop sign or everyone finishes. Well, the first question is where to put stop signs, right? Prior work tries to put stop signs at all memory accesses, which led to really large search space and also very slow to run. And our solution is, our observation is that you only need to put stop signs before concurrency primitives. And it gives, of course, it gives us a very small search space, but the question is, am I going to miss bugs? Well, in fact, it won't because if your program is data race free. So we provide a proof in our extended version of the paper. And if you combine Fray with any mature data race detectors, then you will not miss any bugs. The second question is how to put stop signs. Well, so one way to do that, you can just put some sleeps in your program. Again, non-deterministic and also slow to run. And our solution is to put shadow locks. Idea is very simple. We add additional locks in your application so that based on this cooperative locking and unlocking mechanism, we can achieve both deterministic and which is also fast, very fast. I can't really go into about how shadow locks are designed. I'm going to just give you some high-level intuitions. Shadow locks enforces this sequential execution, and we control the lock and unlock order to control the execution of your program. And we formally model the shadow lock behavior based for all concurrency primitives under Java utility concurrent, and we also provide both soundness and completeness of the search space. And going back to the prior research, we not only support this random walk search strategy, we also support all the searching strategies proposed by prior research. So going back to the question, how am I going to test these softwares? And this is the way we evaluate our system. We collect all concurrency tests in the existing software, and we just run them again with Fray. By just running them, we can find already 363 unit tests can fail under certain thread interleaving, which led to 19 new bugs reported and 15 fixed so far. And some exciting news is that POS actually works the best in terms of bug finding capabilities. And the developers can't really access those algorithms just because of the lacking of this testing platform. So we got some very positive feedback from the developers. After publishing Fray was on the Hacker News front page a couple times. And also, we helped the developer fixing the Lucene bug. And after we fixed the bug, the Lucene developers were very happy, and they invited us to write a blog post about how Fray helped them diagnosing this bug. And after releasing Fray was we got requests from developers from Elasticsearch, Amazon, and Antithesis. They all expressed their interest in integrating Fray into their system. So yes, this concludes my talk today. And Fray is a general purpose efficient platform for JVM concurrency testing. And we open source Fray, and we publish Fray on create on Maven and as Nix Flake packages. And last but not least, I'm Leo, and I work on debugging and testing cloud systems. So you can see my prior work here, and I'm looking for tenure-track faculty jobs. And thank you.
Thank you much for the talk. We have, I think, quite a lot of time for questions.
Thank you for the great talk. So a question about how you model and control the determinism. You said you use locks. Is it possible that there are certain data structures in the concurrent library or the JDK which requires more fine-grained control than just locks? It actually supports concurrency.
Yes.
How do you deal with this?
That's a very good question. Using locks is like a very high-level idea. So we actually designed the semantic of the locks based on the concurrency primitives. Basically, the way you are locking and unlocking those shadow locks are very different based on the concurrency primitives they are controlling. So that's one part of the contribution I couldn't mention in the presentation due to the time limit, but feel free to check out our paper about how we design this. Thanks. Yep.
Hello, Yakov Skolokasis from University of Crete. I have two questions. The first one is about, is Fray garbage collection agnostic, so it plays with all garbage collectors?
Yes, the answer is yes.
Okay, and the second question is that you instrument write and read and write load and stores actually post barriers and read barriers in the interpreter and all the types of JIT compilation with Fray.
So is a question about whether JIT compilation will affect how we do this lock? The answer is no. Actually, we perform this in Java. It gives you this nice property where you can instrument the application before a class is loaded, so that after we perform the instrumentation, the JIT compilation will consider our instrumentation as well. So when they do the JIT compilation, it will not affect how we perform the instrumentation, and it doesn't really affect how we control the concurrency.
Okay, and the third question, and I'm finished. Does Fray, I'm running it during my application execution or on the side? And if on the side, the testing, how it generates the inputs to test all the cases that the execution path can go?
So we do provide a sound and complete modeling of the search space, but currently we use random search strategies like PCT, POS, and random walk to decide which thread to run. Not really because it's just because the search space is huge, so give you some idea about the test we run. For Lucene tests, it usually take like 5 or 6 seconds to run for one iteration. So if we do systematic exploration, it's just too slow for us to explore all possible thread interleavings.
Okay. Thank you very much.
Thank you.
For more questions, yeah.
Okay, hello, thanks for the talk. So I would like to ask about where you insert logs. So you said you insert them on any operations which touch anything from Java util concurrent, right?
Yep.
So do you also insert them when there's a read or write a volatile variable?
Yes, we read and write to volatile variable. We'll also introduce happens before relationship in the Java language. And also atomic variables, they also introduce happens before relationship. We'll also handle some unsafe operations as well.
Okay, thank you.
Yep.
Thank you. Yeah, I think we have 1 more minute for a question. I want to ask, did you find any real bug on system, and did you report them? Because before you show like some reaction from the developers, if you find any real bug, did you report them and how the developer reacted?
So yeah, that's actually very interesting. So we reported these bugs usually after we report these bugs, it takes really long time for them to come back. So not really because they can reproduce them. It's actually because even though they can reproduce them, they still can't really figure out what the root cause of them. Just because the execution is very long, and also like try to narrow down the root cause take time for them. So I feel this is going to be our next step. Like we are going to think about how we can make improved ways to help developers to diagnose those concurrency issues.
Thank you.